one of the most important numbers in our understanding of the universe, is the present value of the Hubble constant. The Hubble constant is a number which belongs to a branch of physics termed cosmology. Cosmology relies upon the Hubble constant to tell us how big the observable universe actually is, via the measurement of its rate of expansion. The typical unit of measure for the Hubble constant is kilometer per second per megaparsec. That is, the velocity of expansion, per very large distance. However, not all is well in the house of Hubble and a great mystery has revealed itself. In this episode, we will explore this mystery and resolve it, all from the experimentally verified particle physics equations we have presented in previous episodes. So, let's get into it. What is the Hubble constant? Well, as we just mentioned, the Hubble constant is a measure of the speed of cosmological expansion, that is, how fast is the universe expanding, expressed as kilometers per second, over a very large distance, termed megaparsec. The Hubble constant is termed constant because it is assumed that it does not vary over distance. However, it is expected to have varied over time. We should emphasize in the strongest possible language, that the Hubble constant, actually being constant across distances, is an extremely significant assumption made by the broader scientific community, which is not based in any scientific fact whatsoever. It is a predominantly uncontested and automatically accepted position, that the Hubble constant is spatially constant, and that all points in space are moving apart at the same rate. In this episode, we shall challenge this position, demonstrating that the so-called Hubble tension does not exist. Huh? Hubble what? Hubble tension? What's that? The Hubble tension refers to the disagreement in results between the two key methods for measuring the value of the Hubble constant. The oldest method is termed the cosmic distance ladder method, and involves converting the brightness of objects in the night sky into a value for the Hubble constant. In 2001, it was measured to be approximately 72 km per second per megaparsec, and then measured again many years later as 70 km per second per megaparsec. The measurement at 72 involve a type of star called Cepheids, whilst the measurement at 70 involve a type of star called red giants. However, the difference between these two measurements isn't really the problem. The problem arrived in 2013 when the second method, termed the cosmic microwave background radiation power spectrum method, measured a value of 67 km per second per megaparsec. The second method involved utilizing satellites to measure very small fluctuations in the temperature of space-time, and converting it into a value for the Hubble constant. But how can space-time have a temperature? Well, it has a temperature because microwaves are moving through space-time, in every direction, which are left over from the Big Bang. These microwaves have a specific wavelength we can measure, and this wavelength can be converted to a value of temperature. Just like black-body radiation. As already mentioned, these very small fluctuations in space-time temperature are converted to a value for the Hubble constant. But, this power spectrum value is statistically different enough from the stellar values, for a problem to exist. This problem is termed the Hubble tension. In this episode, we're going to derive the present values of cosmic distance ladder and power spectrum Hubble constants, utilizing the same particle physics equation. Because all of our results are calculated from the same equation, the Hubble tension is shown not to exist. But first, we'll need to establish some fundamental principles. A fundamental principle we need to establish is the concept of electrogravity-magnetic flux density. That is, the gravitational power being radiated through a surface area at a specific frequency. The unit of measure applied to electrogravity-magnetic flux density is watts per square meter per hertz, also known as Genskis. A Genski is the unit of radiation density associated with radio astronomy, whereby the electromagnetic signals from celestial objects are sampled and interpreted. Now that we have established the similarity between electrogravity-magnetic and radio flux densities, we'll utilize the illustration shown as a pathway to the Hubble constant. Let's consider a supermassive Schwarzschild black hole of cosmological mass. As demonstrated in episode 9, the mass density and radius of the singularity at its core is given by the results shown. The singularity is radiating gravitons, that is, it is radiating conjugate photon pairs which are being absorbed by the quantum vacuum, in accordance with the inverse square law. So, what is the gravitational radiation intensity being emitted by the singularity, when it reaches the inner surface of the event horizon at the Schwarzschild radius? This is actually a critically important question in the pathway to the Hubble constant, as we shall see. When we take the particle physics equation derived in episode 5, and extract the electrogravimetric flux density from it, we see that the reduction in flux density between the surface of the singularity and the inner surface of the event horizon is 140 orders of magnitude. Very clearly, this is an enormous change. And it's this change which becomes the subject of the next step in the derivation of the Hubble constant. The theoretical example we presented on the preceding slide is very clearly and very obviously non-physical. A supermassive Schwarzschild black hole of cosmological mass does not exist and could never be experimentally observed. If it did exist, there wouldn't be any room left in the universe for anything else. However, what the example presented does show is that the electrogravimetric flux density at the instant of the Big Bang was very much greater than it is today. But what could its value be today? Well, we assert that its present value is buried within the cosmic microwave background radiation, and the extraction of that value results in the Hubble constant, as we shall see. Firstly, we shall assume that the transition of electrogravimetric flux density from the Big Bang to the present day is information buried within the cosmic microwave background radiation, which has decayed logarithmically due to cosmological expansion. Hence, it follows that the relationship between the initial and final states of the electrogravimetric flux density may be expressed by K sub u as shown. Moreover, if we define the initial state in terms of the final state, that is, R sub 2 and M sub 2, then we have generalized the solution to K sub u in terms of the final state, which contains information relating to the cosmic microwave background radiation. We can test how well this technique has worked via an example calculation. If the value for lambda sub y is reasonably similar to lambda sub x, then we can move forward with the derivation. As we can see, the value for lambda sub y is within 2 orders of magnitude of lambda sub x. Hence, we consider this result to be perfectly fine. If required, we encourage viewers to review episode 9 to better appreciate the significance of lambda sub x. As we continue the derivation, we arrive at a form of K sub u, explicitly in terms of the final state. However, we have one more step to execute in order to complete the derivation of this function. Next, we'll include a scale factor into the final state. That is, we'll include a scale factor into R sub 2 and M sub 2. We have now arrived at the last step in the derivation of K sub u. It is termed the cosmological expansion function, and has been formulated utilizing the particle physics equations derived in previous episodes. By injecting the appropriate substitutions and executing some mathematical gymnastics, we obtain a representation for the cosmological expansion function which includes a final state Planck scale factor. The effect of the final state Planck scale factor will become very obvious when we evaluate the cosmological expansion function in the coming slides, but what is its purpose? To understand its purpose, we must revisit the manner in which the cosmological expansion function is derived. If you recall, we commenced with a singularity at the center of a Schwarzschild black hole of cosmological mass, then determined the electrogravimetric flux density transition from the surface of the singularity to the inner surface at the event horizon. That is, across the Schwarzschild radius. However, there is no reason why the physical manifestation of the Planck scale should be constant across the Schwarzschild radius in the theoretical example we have utilized. If we expect this to be true, then we are making assumptions. That is, there are no reasons why it should be a valid assumption. Any changes in the final state Planck scale factor yielding significantly different values of experimentally verified Hubble constant is physical evidence that the Hubble constant is not actually spatially constant. In other words, the inclusion of a final state Planck scale factor provides us with an opportunity to determine if the Hubble constant is invariant across space-time, or in fact, variant, depending upon the objects we are observing. Let's now utilize the cosmological expansion function to finalize the derivation of the Hubble constant. Two of the most important engineering concepts of the 20th century are Buckingham-II-Theory and the principles of dynamic, kinematic and geometric similarity. Without these concepts, aviation and refrigeration, amongst many other disciplines, would not exist in the manner we appreciate nowadays. In fundamental terms, these engineering tools enable us to compare two systems of differing scales. This means that if one system may be completely described, then both systems may be described as scalar multiples of each other. We shall exploit this geometric property of reality to derive the Hubble constant. In episode 8, we established a periodic table of harmonic solutions. The basic principle underpinning this concept is that fundamental particles may be represented as harmonic multiples of an arbitrarily selected reference particle. This means that two singularities may also be represented in this way, or just one singularity from two different perspectives. For example, from an initial radius to a final radius. In this illustration, we see two systems depicted. Each system represents a sphere. Utilizing Buckingham-II-Theory and dimensional similarity, we equate the radial growth of these spheres over Hubble time, to accurately derive the astronomical Hubble constant, that is, the cosmic distance ladder measurement, as well as the cosmological Hubble constant, that is, the cosmic microwave background radiation power spectrum measurement. Please try to visualize this illustration in your mind's eye, as much as possible. We already have a solution for the cosmological expansion function, so now we need a solution for the fundamental particle harmonics equation established in episode 8. Firstly, to apply this equation, we need to select a reference particle. Typically, we define R sub 2 and M sub 2 as our reference particle. Next, let subscript 1 denote initial conditions, and subscript 2 denote final conditions. Let's now compress the virial mass of an arbitrary galaxy into a singularity of Planck scale mass density. Virial mass represents the total galactic mass which is gravitationally bound together. Once we've done this, let's recall an earlier slide where we considered the singularity of a Schwarzschild black hole. We're now going to repeat the process, but this time using the galactic singularity instead of the whole universe, and most importantly, we'll be using the harmonic representation of fundamental particle equation instead of the electrogravity-magnetic flux density equation. Basically, what we're communicating is that a singularity of cosmological mass is dynamically, kinematically and geometrically similar to a singularity of galactic virial mass. Therefore, because these two singularities are dimensionally similar, we can utilize Buckingham-II-Theory to scale from one analogy to the other, over Hubble time. So, the initial mass must equal the final mass, and we can now relate the harmonic representation of fundamental particles to the electrogravity-magnetic flux density by equating the cosmological expansion function to the radii ratio shown. Once we have reached this point in the solution pathway, only one more significant step remains. For this, we shall assume that the ninth power of the harmonic ratio is equal to the minimum gravitational lifetime of starving matter, that is, T sub L, divided by the Hubble age. The motivation for this assumption is founded upon the premise that only a single harmonic mode existed within the cosmos at the instant of the Big Bang, which then bifurcated into many modes after Hubble time. If this assumption is incorrect, it will produce obviously inaccurate results when calculating the Hubble constant. From this point, the remainder of the derivation is a simple matter of algebraic substitution, yielding an expression for the present-epoch Hubble constant. Now that we have a solution, how do we test it? Well, we need to select a galaxy and an observational radius. Both of these selections should be very obvious. Our galactic reference should be the Milky Way, and our observational radius should be the solar distance from the galactic center. Why don't we utilize the virial radius, given that we're utilizing virial mass? Simple. Because humanity has not executed any measurements from the location of the virial radius, only from R sub 0. Evaluating our present-epoch Hubble constant equation with the specified inputs produces astonishing results, precisely correlating to experimental observation of the astronomical Hubble constant, that is, the cosmic distance ladder measurement. However, We have not accounted for the cosmological Hubble constant, that is, the cosmic microwave background radiation power spectrum measurement. But do not worry, we shall definitely do this. For now, we will analyze these results on the next slide. Once our analysis is complete, we will be perfectly positioned to derive the cosmological Hubble constant, which has also been experimentally validated. When we compare the results obtained to an authoritative source from the University of Chicago, we yield an astonishing outcome. Not only have we been able to derive the cosmic distance ladder measurements of the Hubble constant precisely, we're also able to derive both primary forms from the same equation. As evident, we are able to derive the Cepheid and red giant results simultaneously. And this has all been achieved via particle physics equations. This is a highly significant outcome and should not be dismissed. In these results, we have demonstrated that the Hubble tension does not exist with respect to cosmic distance ladder determinations of the Hubble constant. Moreover, these results confirm that the Hubble constant is, in fact, not spatially constant at all. Our results confirm that the Hubble constant, as measured, will depend upon the gravitational location of the celestial body being observed. Equally importantly, our results also show that if we have, or double, the galactic virial mass, our results do not significantly change. Hence, the solution for the astronomical Hubble constant derived is robust. Next, we will investigate what these results mean and how it takes us to the cosmological Hubble constant. That is, the Hubble constant is measured via the cosmic microwave background radiation power spectrum. The results we obtained are so astonishing that they warrant greater scrutiny, so let's do a deep dive into the root cause. The way we'll achieve this will be to express our equations in a slightly different form. The form we're going to use will make it very easy to see precisely how the final state Planck scale factor contributes to the solution. We must emphasize that, although these forms appear different, they are exactly equal, as proven by the numerical results shown. We can see in the reconstituted cosmological expansion function, that the final state Planck scale factor in the mass domain, is half the value of the radial domain. The reason for this is to mimic the final state Planck scale factor associated with the maximum permissible mass density for the supermassive Schwarzschild black hole, appearing on slide 4. A very obvious and important question is, what does the value of St sub k represent? Well, St sub k refers to the contribution of Planck scaling upon the dimensions of the galactic reference particle. That is, higher values denote greater scaling. Or in other words, the physical dimensions of the galactic reference particle are scaled in the radial and mass domains by St sub k, mimicking the condition of maximum permissible mass density for a supermassive Schwarzschild black hole of cosmological mass. A critically important feature of the astronomical Hubble constant is that the maximum permissible mass density has been set to a higher limit, as shown. Please keep this in mind as we move forward in order to calculate the cosmological Hubble constant. To calculate the cosmological Hubble constant, we utilize the same equation as we did for the astronomical Hubble constant, which, of course, was derived from particle physics equations. However, to calculate the cosmological Hubble constant, we shall make two very specific changes. Firstly, we remove the half-ratio coefficient relating the mass domain to the radial domain, and replace it with a 1-to-1 relationship. This means that the relationship between Planck length and Planck mass is equal. That is, the Planck mass domain changes in the same way and at the same rate as the Planck radial domain. The second thing we do is match the maximum permissible mass density condition of the galactic reference particle to the maximum permissible mass density condition of the supermassive Schwarzschild black hole of cosmological mass, depicted on slide 4. This means that we are enforcing dynamic, kinematic and geometric similarity between the singularity associated with our galactic reference particle, and the singularity at the instant of the Big Bang. Once again, we see that the results obtained are astonishing. The correlation between our results and the experimental measurement published by the Particle Data Group is almost miraculous. The fact that we are able to calculate both forms of Hubble constant from a single equation is confirmation that the so-called Hubble tension does not exist, that is, no gap in our understanding of astrophysics or cosmology exists. Moreover, The fact that we are able to produce both forms of Hubble constant, without fudge factors, that is, only utilizing exact solutions as appearing in the bottom right-hand corner of the screen, also speaks volumes. However, one important factor which the cosmological Hubble constant is sensitive to, is the choice of galactic mass. Why is this important? It is important because the basis of the measurement of the cosmological Hubble constant from the cosmic microwave background radiation power spectrum, is the temperature of the universe. Therefore, in order to calculate the cosmological Hubble constant, we must utilize a value of galactic mass, which is in thermal equilibrium with the cosmic microwave background radiation. This will actually be the topic of another episode, but for now, we have simply plugged in a value of galactic mass which is known to be cosmic microwave background radiation constrained, as shown. To many people, the value of cosmological Hubble constant calculated utilizing the Wikipedia value of galactic mass, that is, 66.8 km per second per megaparsec, is good enough, but not for us. Electrogravimagnetics is an exceptionally more accurate tool than most others in cosmology, so to us, a value of 66.8 is extremely rough. Let's now summarize what we have covered. The journey through this episode has been arduous, but the rewards have been well worth the effort. The correlation of our results to experimental verification is astonishing and should not be dismissed. The primary tools utilized to achieve this outcome has been Buckingham-II-Theory and dimensional analysis techniques. For viewers unfamiliar with these standard engineering tools, we recommend that you undertake the appropriate course of study. The key achievements in this episode are fourfold. Number 1, the derivation of the experimentally verified cosmic distance ladder Hubble constant, that is, the astronomical Hubble constant. Number 2, utilizing the same equation, we derived the experimentally verified power spectrum Hubble constant, that is, the cosmological Hubble constant. Number 3, we eliminated the Hubble tension problem by producing both sets of experimentally verified results from a single equation. And lastly, number 4, we unified particle physics with cosmology. In addition, and of particular significance, all of the non-physical inputs we have utilized are all exact analytical solutions. This in itself is extremely impressive. No fine-tuning, retrofitting or reverse engineering has been applied at any stage. The equations and results presented have all been forwardly derived, as good science should be. For viewers wishing to consult literature relevant to this episode, you may do so by accessing the links shown.